So in this video we go over additional examples covering the addition rules. Alright, so we have this situation in which a survey found that 62% of the household surveyed had internet access, 68% had cable TV, and 43% had both. The question is to find the probability that a randomly selected household in the survey has either internet or cable. Okay, so in this case what I would do first is to draw what we call a Venn diagram, which is what we have been doing in the previous examples. So I'm going to do something like this. In this case I'm going to have intersecting bubbles, intersecting sets, because we have the situation in which a percent have both of the services at the same time. So in this case we have with blue, so 62% of the households have internet and 68% had cable, and at the same time 43% have both. That is going to be our intersection. Okay, so let's fill in the bubbles here. One color and then the other color. Okay, so in this case blue represents the percent of people who have internet, which in this case is 0.62. I'm going to convert those percentages to decimals. And then people who have cable TV, 0.68. And then in intersection it's both, which is a total of 43% or 0.43. So when we define our events, we are going to have that A will be internet, B will be cable TV, and the combination of both will be A and B. Oops, just symbol and, not an A. And let me erase this so it doesn't cause any trouble here. And I will use purple color, which is a combination of this, which will be both. So when we find the probability for this, so they are really asking us to find the probability that either A or B, which in this case will be the addition of the two probabilities, but in this case minus some intersections, because notice we have overlaps here. So let's just plug in the numbers. That's going to be 0.62 plus 0.68 and minus 0.43, giving us a total of 0.87, which is the probability to have either one or the other. Doesn't have to specify which one is it. Okay, so a very similar situation. Well, so in this case let me draw another Venn diagram. So we have the probability out of that we have the at a local university 62% of the students are undergraduates and 55% are male, and 48% of the undergraduate students are male. That is, we have some intersections. Some undergraduates, male, and 48, 0.48, no, 55. And the intersection is 0.48. Okay, we are going to use essentially the same idea. Okay, undergraduates are going to be blue, and male students going to be pink. Combining, we get the intersection, which is purple, and we are going to define the events in a very similar way. So event A, which is the number of students that are undergraduates. Event B will be the number of students that are male. And we have the intersection of the situation, which in this case I'm going to use purple for this. So A intersection B will be both male undergraduate. So when we find the probability that a randomly selected student is either male or undergraduate, that'll be, we're going to use the usual formula, well, P of either A or B, either one or the other, will be the addition of both probabilities. But in this case, again, we are going to subtract overlaps to avoid counting them twice. Let's plug in the numbers. 0.62 plus 0.55 minus 0.48, which will give us a total of 0.69. Okay. Now we have a very typical problem in which they give us what we call contingency tables, or sometimes we call this two-way tables. Let's write that down. Two-way tables. Okay, so in this case we are given two rows, well, rows and columns relating characteristics of some situation. In this case, we have the total data of a local dealership that sells sedans and SUVs, which some of them are new, some of them are used. Okay, so we are going to use this information to find different probabilities. For example, determine the probability that a random selected car is new. Well, first of all, it would be what we do in these situations is add all the rows and the columns. Okay, so I'm going to add the rows, the columns. 24 plus 9, that's a 33, and the second column, that adds up to 27. The second row adds up to 39, and the second row is 21. Adding both totals, either way, the horizontal way or the vertical way, it should give you the same grand total, which is 60. That's the grand total. Okay, so in this case, how are we going to find the probability that a random selected car is new? Okay, so in this case, well, let's define the event A to be a new car, And in this case, it's not being specified whether this car is a sedan or an SUV, just any new car. So I'm gonna go to the total number of successes, which is the number of total new cars, that is P of A equals to 39 divided by 60. And that is the probability, which reduces to 13 over 20. For letter B, let's determine the probability that a randomly selected car is a sedan. So in this case, I'm going to go to the total number of sedans, whether these are new or used, it doesn't matter. Okay, that doesn't matter. So I only need the car to be a sedan. The probability for that to occur is 33 out of 60, which reduces to 11 over 20. For letter C, let's determine the probability that a randomly selected car is a new sedan. Notice in this case, new sedan, we are combining two elements from the row and a column. So in this case, we are going to define two events. We are going to define event A, which is new, and event B, which is sedan. So in this case, we are going to use a rule that we haven't used before, which is the AND rule, because in this case, when we say new sedan, well, we are combining both characteristics at the same time. Both events are occurring at the same time. What do we mean by that? Well, so in this case, this is how we solve this problem. So the probability that A, and in this case and, not an or, like the other problems that we have done earlier, equals the intersection between new and sedan. So how many are there in the intersection? In the intersection, there are a total of 24 out of 60, which reduces in this case to 2/5. You reduce this to lowest terms. Okay, so that's an example in which we do these so-called contingency tables or two-way tables. So there's another example I would like to do. I'm gonna make it up in a way. So let's see. So and I like this problem because of the way it is worded. So we are gonna have a situation in which, let me retrieve the problem. So we have that if SDSU football team has a 10% chance, so 10% probability rather, of winning Saturday's game. A 30% probability of winning in 2 weeks and 65% of losing both. Okay. What is the probability of winning exactly one game? Alright, so in this case, let's define the three events that we have. Alright, so I'm going to define event A, which is winning Saturday. I'm going to define B, which is winning in 2 weeks. And letter C, if they're lucky enough to win both. Because it's possible, so in this case we are going to have an intersection of events. Okay, so let's find the probability. Okay, let me write this again as well with their corresponding probabilities. But the probability of winning Saturday is 10%, which is 0.10. The probability of winning in 2 weeks is 30%, which is 0.3. We have a problem here with the probability of winning both, because in this case they are giving us the probability of losing both. Okay, if we know the probability of losing both from here by complement, we can find the probability of winning both, which in this case is 0.35. Hopefully this doesn't freak you out. Where am I getting this 0.35? Because in this case I need the information for winning both. I don't not the probability for losing both. I mean, it's good to know the probability for losing both, because from there, using that piece of information as our starting point by complement, we get the other piece of information. So the probability of either A or B equals probability of A, probability of B, minus the intersection. So in this case, just put the number 0.1 plus 0.3 minus 0.35. So we are going to have in this case 0.40 minus 0.35, that's going to be 0.05. If I'm not mistaken, if not otherwise, let me do the calculation again. 0.1 plus 0.3 minus 0.35, and that is correct. 0.05, which is barely 5% chance. So it looks like the SDSU game is not, the SDSU football team is not doing very well. Okay, so this is the end of this video. I'll see you in another video.